name is Puddu and I'm a PhD student at ETH Zurich. In this video, I'm going to present our paper titled Frontal Attack Leaking Control Flow in SGX via the CPU frontend. As our attack exploits SGX, I'm going to start off by explaining the SGX system model. SGX assumes that an attacker has completely compromised the system, and yet it tries to protect an application running in such a compromised environment. This application is protected in terms of integrity and confidentiality thanks to primitives provided by the CPU. However, there are still ways in which one can go about extracting secrets from such a protected environment. And to explain this, I'm going to use the code shown on this slide as a victim code. So in this code, we have a branching condition on a secret, and when the secret is 1, we execute on the left path shown in blue. And when the secret is 0, we execute on the false path shown in pink. What an attacker can do to extract the secret is to leverage shared resources in the system. One of these resources is the cache. And the way this works is that if we are executing on the true path, we might access one cache line shown here in blue, while when we are executing on the other path, we might access a different one. And through cache attacks, the attacker can see which cache line was accessed and therefore recover the secret condition. However, this does not work when both accesses happen within the same cache line, since the attacker cannot observe a sub-cache line can write. Another attack that can be done against this code leverages the branch prediction unit, which is used to aid speculation. So for instance, when we execute this code, after the branch condition, some information about the execution of the branch might be stored in the last branch record. For instance, here we store the fact that it was taken, and attackers can infer the value stored on this buffer. Thankfully, compiler mitigations exist that produce branching code that doesn't update the structure of the CPU. Nemesis follows a different approach from the previous two attacks in that it leverages interrupts that the attacker can now issue because it controls the operating system. Through interrupts, the attacker can time the execution of each instruction. And if one of the instructions, for instance, is a multiplication, in this case, then the attacker will see that this one takes a longer time than an addition, therefore he knows that the execution was in the true path. However, this doesn't help with the victim code that I'm using as an example because the same instructions are present in both paths. Another approach that leverages interrupt is the attack called copycat. And what copycat does, instead, it counts the instructions that were executed. So if we have 2 instructions on the false path and 3 on the true path, then the attacker can recover the secret. However, this does not help with the victim code here because both paths have the same number of instructions. One of the reasons why we're looking at this particular victim code pattern is that it's found on several cryptographic libraries. And the reason for that is that they assume that if you have the same instructions, it will take the same amount of time for them to execute. It doesn't matter in which branch they are. So an attacker that is able to time the execution won't be able to see which branch was executed. We, however, show that this assumption does not always hold, and particularly doesn't hold when the attacker can interrupt each instruction. So what it looks like is something like this. The attacker will start the victim branch and then it will interrupt it right after the first instruction. And it will do the same for each of the instructions until the execution terminates. And with this, the attacker is actually able to see timing differences in the execution. We use this observation to exploit 2 commonly used libraries inside SGX. One of them is Intel's IPP cryptography library, which claims to be side-channel resistant. However, it still contains a balanced branch on some of its functions, for instance, when big numbers are compared. And when we time the execution of that comparison, we see the distribution shown here on the right, where on the x-axis we have the execution time in cycles, and on the y-axis we have the density of the distribution. So the yellow curve represents the distribution of a memory write in the smaller than path, and the blue curve represents the same memory write, except this time executed on the bigger than path. So as you can be seen, the attacker can distinguish when these two branches are executed, so it can recover the result of the computation. And this allowed us to leak 25% of a secret that was used on a loop in this comparison. Another library that we exploited is the ARM embed-TLS library, and in there we exploited two functions. The first one is the Montgomery multiplication, which is mostly constant time way of multiplying big numbers, except there is a secret-dependent subtraction at the end of the multiplication. And when we time the balance branch that is put to mitigate timing attacks in that in the computation, we see the distribution shown here, which again, it's different despite the fact that we are measuring the same instruction. So with that, we were able to leak 83% of these subtractions, which are related to the inputs of the multiplication, which are secrets. So another function that we exploited is the RSA key generation. And in there, at some point, GCD computation on some secrets is performed, and the GCD computation has a secret branch. And we were able to measure that branch, and with that recover the key that was being generated within seconds on 65% of the runs. And finally, I want to mention that this actually worked on all SGX architectures that we tested up to 10th gen, with some differences depending on the architecture and the microcode, but this is discussed more in the paper. And finally, the attack worked better with SMT disable, despite the fact that it's usually a good security practice to have it disabled because it prevents other attacks. To give an idea about which parts of a victim binary might be vulnerable to our attack, I'm going to show how the attack performs with the code shown on this slide. This code consists of 25 repeating additions and memory writes, and there are two identical branches like before, and which branch is executed depends on a secret. Now, what we are gonna change with this code and check the results of the attack with these changes is the alignment of the branches. And with alignment X, for the if branch, I mean that the first instruction, the addition, will start at an address that ends with X. So if X is 5, the valid starting addresses could be 15 or 25, but not 26. Now, with this in mind, I'm going to show the results of the attack, where we have the various alignments of the if branch on the x-axis and the elements for the else branch on the y-axis. And darker colors represent higher success rates in this heat map. So as it can be seen, there are differences based on the alignment. So this is one of the determining factors on whether the attack will succeed or not. And perhaps more interestingly, the attack success rates repeat every 16 bytes. So we can essentially split this heat map into 4 quadrants of length 16. And the success rates inside these quadrants are essentially the same. Another thing to notice here is that along the diagonal, the success rate is 50%, meaning it's as good as a random guess, but not better. So when the alignment of the two branches is the same, the attack is not successful. In the paper, we provide a more comprehensive list of requirements and limitations for the attack. But for now, I'm going to discuss why we are seeing this 16 bytes repetition for the attack success rate. And to do that, I'm going to show what happens to the CPU pipeline as we are interrupting each instruction in this code snippet shown on the left. The binary of this code is shown inside this red rectangle, which represents the L1 instruction cache. The first stage of the pipeline is the instruction fetch and predicode. What this module does is it fetches 16 bytes from the L1 cache that is going to try to predicode. And importantly, the 16 bytes that are fetched can only start at a multiple of 16. So the predicode then will try to recognize where instructions start and where they end. And in this case, it has recognized 3 instructions, and it knows that there is 1 instruction that is incomplete. These 3 instructions are then going to be forwarded to the next stages, and eventually they are going to reach the backend. Now note that the first instructions to reach the backend are actually the ones that were present in the first 16-byte block that was pre-decoded in the front end. Now, these instructions are also going to be the first ones that are going to be sent to the execution units, and maybe one of them will complete. And then as we are interrupting after each instructions, when the interrupt arrives, they are going to be flushed. However, the CPU still needs to retire in order and to provide some consistency to the developers. So the first instruction is still going to be retired. And after it completes, we can advance the program counter and serve the interrupt. If we look at what happens in the else branch, now this branch is differently aligned from the if branch. So the first 16-byte block that reaches the front end actually only contains one usable instruction. And this instruction again travels through the front end and is the first one to reach the reorder buffer. If we look at which instructions reach the backend first after each interrupt, we will obtain something like shown in the table in this slide. That is, after the first instruction, we get these micro operations in the backend. And then after the second one, we get the ones in the second row, and so on and so forth. So the interesting thing here is that these differences emerge because the first 16-byte block that we're getting in the fetch and predicate module has to be statically aligned as 16 bytes. And out of these 4 instructions that we interrupted, 3 of them had different instructions reaching the backend for the first time after the interrupt. And this might cause the interrupt handling to actually be faster or slower, depending on which instructions need to be retired and what things need to be reverted. I'm going to conclude by showing some of the ways that one can go about defending against our attack. And the first one to mention is a principal approach that completely avoids any secret dependent branches altogether. And the reason why this is good is that it also protects against other side channel attacks. We also evaluated some ad hoc solutions because these are simpler to implement and don't require rewriting your code. So the simplest one is to just align the code to the same offset modulo 16, because as we have seen, the attack success rates for this particular code are very low. We have evaluated the space overhead and the performance overhead of this defense, and we have noticed that the space overhead is very small. And interestingly, with this defense enabled, sometimes the code was actually faster than without the defense. So with that, I would like to thank you for your attention.